Hi, this is Dr. Morgan, and I'd like to go over the Unit 5 review with you and work all the problems, so hopefully we can be better prepared for our Unit 5 test. Our first problem asks us to evaluate an exponential function 16 times 2 to the x power when x is minus 3. So the first thing we're going to do is substitute for x minus 3. So f of negative 3 is 16 times 2 to the negative 3 power. The next step, we have to recognize what is a negative exponent. We remember that a positive exponent, for example, if I had 3 squared, we recognize that that square means to multiply 3 times itself 2 times. It's repeated multiplication. However, a negative exponent never means a negative number. It means the opposite of repeated multiplication, which means I'm going to divide by 3 2 times. Okay, so in this case we know that a to the n power here is 1 divided by a to the n power. In other words, we take the reciprocal and change it to positive, the exponent to positive. So in our case here, we'll notice that 2 to the minus 3 power is actually 1 over 2 to the positive 3 power. Well, 2 to the 3 power, 2 times 2 times 2 is 8. So we have 16 divided by 8. So finally we find that f of minus 3 is actually 2, and that's our answer. The second problem simply tests us on our ability to change negative exponents to positive exponents. In the first one, we remember that any number to the negative power means I simply flip it over, take the reciprocal, and change it to positive. So 8 to the negative 1 means divide by 8 one time, or simply 1 over 8. Likewise, 12 to the minus 2 means I divide by 12 2 times. So 12 to the minus 2 is 1 over 12 squared, or 1 over 144. Likewise, if I have a situation in which the negative is in the exponent, actually when I end up here, instead of it, you notice on the first ones here, we went down. Well, when it's in the denominator, we're actually going to go up. So it goes up to the numerator. So in this case, 1 over 3 to the minus 2 simply becomes 3 squared, and the answer is 9. Problem 3 asks us which of the following expressions are equivalent to 1. In the first expression, 11 to the 0 power, remember that any number, every non-zero number, a to the 0 is 1. So 11 to the 0 equals 1. And so this answer is equivalent to 1. It's a possible answer. The second one, we need to solve this. And we notice, first of all, the number in the top here, 2 to the minus third, means it's going to go down to the bottom and become 2 to the 2 cubed underneath in that case. Likewise, when we look at the bottom number, remember that in the bottom number, it's going to go up. And so 3 to the minus 2 becomes 3 squared. Now we simplify. 3 squared is 9. 2 cubed is 8. 9 over 8 is our simplification. So that's not equal to 1. Finally, we have 1 over 2 to the 0 power. Again, remember, any number to the 0 power is 1. So 2 to the 0 equals 1, and we get 1 over 1, which is 1. So again, this one works and is equivalent to 1. Problem 4 asks us to write a reasonable equation for each graph shown below. In the first graph, we notice that it's not a straight line, it's curved, and we expect that it's probably an exponential function. That means it'll have the form y equals a times b to the x power, where a is the initial value, or the value that it has when x equals 0, or we could call it the y-intercept, and b is the common ratio. What is the factor being multiplied by each time? In the first case, we notice it crosses the line there at 0, 1. That means when x is 0, y is 1, and so our a, our initial value, is 1. The second point we find, the next point, when x is 1, we have the point 1, 2. So now we can compare these 2 points and say what did 1 get multiplied by to get 2, or we divide them. The 2 divided by the 1, and we see that the ratio is 2 to 1 between those 2 points, and so b is 2. This is simply the factor that multiplies each succeeding factor by 2. So we can write our equation as y equals 1 times 2 to the x, or simply simplify and just write y equals 2 to the x power. Our second graph is obviously a straight line, so it will have the form y equals mx plus b, where m is the slope of the line, the rise over the run, and the y-intercept is b. Let's start by finding the y-intercept. It crosses the y-axis right there at the point 0, minus 4. That's going to mean that b equals minus 4. Our slope then, let's draw a little slope triangle between 2 points we can readily identify. Notice it goes up 4 and over 2, so my slope is 4 divided by 2, rise over run, and that's a positive slope of 2. So we can insert m and b into our equation and discover that our equation is y equals 2x minus 4, and that's a reasonable equation for that line. Our third equation is also a line, and so we do the same thing. Notice that the y-intercept is 0, minus 2. That means b equals negative 2. And our slope, let's draw a slope triangle here, goes down 2 and over 2. So the slope is negative 2 over 2, or negative 1. So now we can plug those into our equation and see that y equals minus 1x minus 2, or we can simplify this to be y equals x minus 2. And that's the equation, the reasonable equation for that line. Problem 5 asks us, what are the values of x that best represent where f of x equals g of x? Well, where f of x equals g of x is wherever they intersect. So notice they intersect right there at that point there. And that's simply the point minus 2, 4. And they also intersect down below here at this point here, and that's the point 1, 1. So those 2 points are solutions for both f of x and g of x. And the question is, what values of x best represent? So the values that best represent then are x equals negative 2 and x equal 1. Those are the 2 values of x where f of x equals g of x. Problem 6 asks this question. A student invests $400 at a rate of 8% per year. What amount of money will the student have after 2 years and then after 5 years? Well, our equation for compound interest says that the balance, A, equals the principal, the amount you start with, times 1.1 plus R, where R is your interest rate you earn each year. And then that's to the t power, or the amount of time in years. So what we need to do is simply plug in our amounts here. A is our amount. P, our principal we start with, is 400. Our rate, 8%, is 800. So remember, percent means per 100, so 8% is 800. Don't put 0.8. That would be 80%, not 8%. And then t is going to either be 2 or 5. So let's put in 2 first for 2 years. Then we have 400 principal times 1 plus the 8%. Because the 1 plus the 8 is because you get to keep your money plus 8% more. And then we're going to do that for 2 years. So in this case, 1.08 to the second power. Square that. That's 1 and 1,664. And we find out that after 2 years, his $400 would be $466.56. Now let's do it if he leaves the money in for 5 years. Well, at 5 years, all that changes is the exponent is 5 now instead of 2. So once again, 1.08 to the fifth power is 1.4, and it goes on and on and on. But we're going to multiply it times 100, and now we're going to round this one off to the nearest cent. So if I round it nearest cent, 3 next to it's a 1, so we're not going to go up. We're going to keep it at 3. So our answer is $587.73. Problem number 7 states that a population of endangered fish decreases exponentially and can be represented by the function f of x equals 1200 times 9300ths to the x power. What's the percentage rate of decay? First of all, we notice that it is a decay. If your factor b is less than 1, between 0 and 1, this is exponential k, and 9300ths is obviously less than k. But what's the rate of decay? Well, the rate of decay is how much less than 100% it is, or how much is the decay factor less than 1. So if I take 1 and I subtract the 9300ths, I find out that it actually went down by 700ths, and that's my annual decay rate. The decay rate is 7% annual decay 100% minus 7% is 93%, or 1 minus 93 hundredths is 7 hundredths. 7% annual decay. Problem 8 asks us to determine how many real solutions there are to each equation. And it says answers may be used more than once. We're either going to have no solution, one solution, or infinite solution. So let's look at the first one. 8 to the x is 64. Well, if you have two numbers with the same base that are equal to each other, then the exponents must be equal. So that means x must be equal to 2. So in this case, there is a solution. 8 squared is 64, so there's one solution. The second one says that 2 to the x power equals negative 1. Now remember, even if we have a negative exponent, it's dividing. Doesn't change it negative. So 2 to the x is never going to be negative. It's always going to be positive. So there's no way that 2 to the x power is ever going to equal negative 9. So in this case, this equation has no solution. Part C, again, we put them together. Recognize that 49 is 7 squared. So if I substitute 7 squared for 49, I get 7 squared to the x power. And by our rule of exponents, 7 squared to the x power is 7 to the 2x. And notice that they're exactly the same. In other words, 2x equals 2x. The exponents are the same. So we see that this is going to be true no matter what the value is of x. And so in this case, this equation is an identity, or it has infinite solution. And finally, 3 to the x minus 1, x plus 1 equals 1 over 9. When we're comparing things, we got to put them as the same base. So I notice that 9 can be written as 3 squared. Okay? Well, 3 squared underneath in the denominator is the same as 3 to the minus 2 power. And now I have two sides with the same base, so I can set the exponents equal. So x plus 1 must equal negative 2. If we subtract 1 from both sides, we find out that x equals minus 3. And so D has one solution. Problem 9 gives us a problem being worked and asks us to choose if it was done correctly or identify where the error occurred. So let's begin working the problem and see if we can find the error or if it's done correctly. First off, I'm looking at these two equations and I notice this large number here, and I notice over here we have a base of 3. So my immediate question is 2,187 some factor of 3? And it is. 3 to the 7th power is 2,187. So if I have 1 over 3 to the 7th power, I can actually write that as a negative exponent and say 1 over 287 is 3 to the negative 7th power. So as a result, I can rewrite this equation this way. 3 to the 2 to the x plus 1 power equals 3 to the minus 7th power. And you notice that it's correct. So step 1 is correct. So now, since these both have the same base, 3 and 3, and they're equal, it means their exponents must be equal. So 2x plus 1 equals minus 7. And at this point, you notice that's where the error occurred. Now let's finish out the problem just to see how it worked. This is a two-step equation, so if I subtract 1 from both sides, I'm going to get 2x equals minus 8. If we divide both sides by 2, we're going to get x equals minus 4, and that's not the solution that they got there. So the error was in step 2, and your answer would have been. Problem 10 gives us the following equation. Negative 2 to the x power equals 10. And what they did to see if they could find a solution was they graphed each side separately. So they took the minus 2x and they graphed this equation right here. Y equals minus 2 to the x power. And then they graphed the other side here, y equals 10. And the question is, do they ever intersect? And if you notice, these two lines are never going to intersect. This one's getting smaller and smaller, and it's never going to reach that point. So the solution occurs where they intersect, and the graphs will never intersect. So there is no solution to this equation. Problem 11 asks us to write the explicit formula for two geometric sequences. The explicit formula, states that the nth term is equal to the first term, and that a to the 1, a subscript 1 means the first term, just like a subscript n means the nth term, times the common ratio to the power of n minus 1. In our book, you may have seen it a little different sometimes, where they wrote it more kind of like in a function notation, and they would describe the nth term by a of n equals the first term, a of 1, and then again times r to the n minus 1. Very similar, but just a difference of writing. So if we want to write a geometric sequence, we only have to find two things. What is the first term, and what is the common ratio? Once we know those two things, we can write the explicit formula. So let's look at the first one. What is the first number here? Well, the first term is 4. So I know that a1 equals 4. Now I just have to find the common ratio. To find the common ratio, I'm simply going to take any two pairs here and divide the second number by the first number. So I have 8 divided by 4, or 16 divided by 8, or 32 divided by 16. They all equal 2 over 1, or just 2. So now I can write, and notice that also tells me how this sequence is being multiplied. 4 times 2 times 2, and the common ratio is telling you what you're multiplying by, and you can determine more. So now we can write our explicit formula by simply substituting this into here and this into here. And so we have an equals 4 times 2 to the n minus 1, and that's our first one. Same thing with the second one. What's our first term? Our first term is 54, so a1 is 54. And now let's look here between them, and notice this time 18 divided by 54 and 6 divided by 18, 2 divided by 1 give us this number 1/3. In other words, what we're doing here, instead of multiplying by 2, we're multiplying by 1/3. Remember that multiplying by 1/3 could also be stated as we're dividing by 3 each time. They're identical. And so now we can complete the thing by plugging 54 into a1 and 1/3 into r. And so we put those numbers in, and there's our second term. The nth term is 54 times 1/3 to the n minus 1 term. Problem 12 gives us an exponential function. F of x equals 3 times 1/4 to the x power. And it asks us to find the range values for a given domain. Remember, domain is always your x values, whereas your range values is your f of x, or sometimes it's stated as your y values. In this case, the x values are given here as -2, -1, 0, and 2. So we're simply going to plug those in for x there and find our answers. So the first one says f of -2 is equal to 3 times 1/4 to the -2 power. Now you need to remember that when we're doing a negative exponents, we used to say you take the reciprocal and change the exponent to positive. So that's going to mean that 1/4, in other words, if I have a over b to the minus n, that's going to be b over a, see the reciprocal, to the positive n. So in this case here, we change 1 over 4 to 4 over 1 and change it to positive 2. So 4 over 1 is simply 4, so 4 squared is 16, and 3 times 16 is 48, and that's our first answer. The next one, similarly, again, it's a negative exponent, -1, so we change it to 4 over 1 to the positive 1, and we simply have 3 times 4, or 12. So f of -1 is 12. F of 0, remember our rule, anything to the 0 power equals 1. So 1/4 to the 0 power is 1, so this is 3 times 1, or 3. And now we get into positive exponents, so we have 3 times 1/4 squared is going to be 3 times 1 over 4 squared, or 3 times 1 over 16, or 3/16. And finally, those are our three answers. The range is 48, 12, 3, and 3 over 16. Problem 13 is an important problem because it asks us what kind of situations can be modeled by an exponential function. Or is it simply a linear function or something else? In problem 1, Matt is paid $15 an hour at his job. So after he works 1 hour, he has $15. When he works a second hour, we add 15, and now he has $30. If he works again another hour, he gets 15 more, now it's 45, etc. And so his work is just simply increasing. Every hour he works, he gets another 15. So this is a linear function because it has a common difference. The common difference means the difference between any two numbers is 15. We're simply adding. So this is a linear function, not an exponential. In the second problem, when we first read it, it says Brandon takes out a simple interest loan. We usually think of interest as exponential, but this is called simple interest. And remember, simple interest means that you pay on the principal only, you don't compound. So, for example, if Brandon takes out $100, he's simply going to pay the interest of $1.80 plus his principal back. So, in this example, if he starts off with $100, then after whatever period he's paying interest on, a month, a week, whatever it is, he's going to owe another $180. And then if he doesn't pay it all back then, he'll owe another $180. And so he's only paying interest on the initial principal, not on the principal plus interest. So in this case, there is a common difference. You're simply adding 8% of the loan each time. And so this, again, is a linear function. It's not an exponential function. In problem C, we also have an interest problem, but this time it's compounded. It's compounded quarterly, which means every 3 months they figure the interest and add it to the balance. So in the first case, he starts with $15,000, but then after a quarter, they add the interest. So it's the original one, $15,000 plus 4%, and so now after 3 months, he's going to owe $15,600. Now, after 3 more months, he'll owe another 4%, but this time the 4% will be based upon what he owed at the quarter. So we have the whole times that, and we end up with $16,224, and it's growing rapidly. You'll notice then that what we have is not a common difference, but we have a common ratio, that each time it's being multiplied by a factor. And when you have that multiplication, that common ratio, then you know you have an exponential function. So we're going to circle C as an example of an exponential function. In problem D, Andrew drains his pool at a rate of 5 gallons per minute. So he's draining, so it's going down 5 gallons every minute. So for example, if he had 2,000 gallons in his pool, then after 1 minute, he'd lose 5 and he'd have 1,995. 5 more minutes, he'd lose 5 more and he'd have 1,990, so on, so on. And so then, therefore, what's happening here is there's a common difference of 5. He's losing 5 each time. So this is not exponential. Once again, this is a linear function. So D is not an example of an exponential function. The last one, it says Steve's collection of insects is doubling each month. Now, doubling means I'm timesing it by 2. So, for example, if Steve had 30, after 1 month, you'd double that and you'd have 60. After another month, you'd double that and have 120, and on and on and on. So in this case, we have a common ratio. In other words, we're multiplying by 2. So this is an exponential function. And so we can circle E as another example of an exponential function. Problem 14 asks us to look at the graph and determine which of these situations, A, B, C, or D, could be modeled by that. So let's look at the graph first. First of all, I want to find out where the beginning point is, the A 0 point. Notice here, when x is 0, my first term is going to be 1. So this is the point 0, 1. So in my equation for a function, y equals a times bx, a has to be 1. Now we find a point that we can identify here. Many of these are hard, but I find a point there. Notice that at this point where x is 4, y is 5. So we're going to look at this and use this to determine if any of these match. So in the first problem, notice that f of 4, if I put x in for 4, I want to see if I get 5. Well, notice 4 to the 4th power is 4th over 3 to the 4th. So 256 to 181, that is definitely not 5. So A doesn't work as a problem. Number B, letter B, says the number of mice decreases 90%. Well, notice that our function is going up. Okay, it's not decreasing, it's increasing. So because this one's decreasing, this can't possibly be our answer. C says f of x equals 2 of x. Now, let's check that f of 4 point again. 2 to the 4th power equals 16, so that's not 5. So f of x equal 2 to the x power is not possible as well. Then the last one says that 3/4 of the plants die every season. Well, if you're dying, you're going down. So that's going to be another decreasing graph, so this one doesn't work. So this particular problem does not have any of these examples, would model the situation on the graph on the left. Problem 15 asks us, how can we determine if a function is exponential growth or exponential decay? The key to this is to look at the base factor b. Here's our equation, and we want to look at this factor b. That's the key that tells you whether you're growing or decaying. If this number is between 0 and 1, it's exponential decay. You can just think about it this way. Let me do a simple one. Let me let b be a be 1 and b be 1/2. If I just let it be 1/2, which is less than 1, what I'm really doing is every time I take a number, like 100, and I multiply it by 1/2, what happens? It gets to be 50. Multiply it by 1/2, it gets to be 25. So if it's between 0 and 1, it's exponential decay. What happens if it's greater than 1? It's exponential growth. So same example, if I do y equal 2 to the x, here this is greater than 1, then I have 100 times 2 is 200, times 2 is 400, and you see now that one's growing, whereas this one was decaying. So the key is, if your b is between 0 and 1, you have decay. If it's greater than 1, you have growth. (16) asks us to simplify this expression, and what it basically means is take all of the negative exponents and make them positive, which usually means this one's going to come down and this one's going to go up. It also means that we get rid of any 0 exponents, which equal 1. So that's going to be our basic strategy on this problem as we go forward. So let's begin. First off, I notice that the 0 exponent equals 1. So I'm going to take the a equals 0 and just simply make it 1. So we eliminated that, and now we just have 3 to the minus 2 times b to the 8th and c to the minus 2. Next, I'm going to realize that any exponent in the numerator can simply go down to the denominator. And so in this case, I'm looking at this one here, 3 to the minus 2. And so we're going to move it down and make it positive. So 3 to the minus 2 goes down and becomes 3 squared. So now we have b to the 8th over 3 squared. And now we just have one left to go. We'll notice that now we have down here, we've got our c to the minus 2. We want to get rid of the minus 2. And so we remember if we have the negative in the denominator, it's going to go up. If I drew that like that, it's going to go up to the top. So this is going to move up and become c squared. And so in our next problem there, we have b to the 8th c squared. And divided by 9. And that is our answer. Notice that we did simplify 3 squared equals 9. So our answer is b to the 8th c squared divided. Number 17, we're asked to solve for x. We have an exponent. X is in our exponent. So the first thing we want to do is we notice we have a 2 to the x power. So we're asking, can we write this one as 2 to some power? And in this case, we do know that 2 times 2 times 2 times 2 equals 8. So in other words, we can write that 2 to the x minus 3 equals 2 to the 3rd power. Now, at this point, we remember that if these two are equal and the bases are equal, then it means that the exponents are equal. So we can set the exponents equal and recognize that x minus 3 equals 3. And now we have a simple equation to solve. We simply undo the subtract 3 from the left side, add 3 to both sides. That's eliminated here, and we end up with x equals 6 as our answer. And if we want to check it out, we can simply notice and say that 2 to the 6 minus 3 equals 2 to the 3rd power, which does indeed equal x, so our answer is correct. Number 18 is a problem similar to one we did earlier. We're being given an exponential function, y equals 25 times 2/10 to the x power, and we want to find the range. The range is all the y's for the given domain for these x's. So we're simply going to plug each of these into this equation, into x, and find out the appropriate values of y. So let's begin. F of minus 2, and I'm going to use the function terminology because I want you to understand this is y when x is minus 2, 25 times 2/10 to the minus 2. Remember that the negative exponent means that we divide by that number, in this case 2 times. So that becomes 1 over negative 2 to the plus 2 power. So we get 25 times 400ths, or we end up with about 625 is the answer to that one. Now we do for negative 1, same thing. And this time it's 1 over 2/10, but just one time. And you see we get 25 divided by 2/10, or the answer is 125. Now we put in 0. Remember that anything to the 0 power is 1, so this is just 25 times 1, or 25. And now we go to the positive. We don't have to change it. 25 times 2/10 is going to be 5. And then squared, or 2, 25 times 2/10 squared is times 0.04 is going to be 1. And so we can identify our range as 625, 125, 25, 5, and 1. That's our range. The last part of the question asks, as the domain increases, as this is going this direction, what's happening to our numbers here? And the answer is they're going down. So the values are decreasing. Problem 19 gives us a typical loan problem. You borrow $7,000 at a 2.5% annual interest rate. How much will you owe after 3 years if you compound it yearly, quarterly, or monthly? Notice each year you're going to only pay 2.5% interest, but it depends on whether they charge it once a year, or quarterly means 4 times a year, or monthly means 12 times a year. Notice they will not charge you 2.5% each time. Here they'll charge you 2.5% one time. Here they'll charge you 2.5% divided by 4, and they'll do it 4 times, so it'll still be equal to 2.5. And here they'll take the 2.5 and divide it by 12, and you'll still end up paying this amount for the year, but you'll be doing it either once a year, 4 times a year, or 12 times a year. That's how the compounding by monthly, yearly, and annually work. So first off, let's remember our formula states that the balance is going to be the principal, $7,000, times our interest rate, which is 1 plus whatever the rate is. This is our 2.5%. And then it's going to be divided by how many times a year do we do this. For compound yearly, that'll be 1. For quarterly, that'll be 4. For monthly, that'll be 12. And then how many times do we do it? Well, t is the number of years. And then we multiply that by n, depending upon, again, 1, 4, or 12, how many times we're actually doing that each year. So let's get started with compounded yearly. This is the easiest one because n is 1. And so notice I simply have 2.5 divided by 1, and I'm going to do it 3 times 3 years, 1 times 3. So we ended with 7,000 times 1.025 to the third power. At this point, we're going to take out our calculators. And if you haven't found the button on the calculator, the way you would do it is you'd take the 1,000.025, punch that in, and then find the key that looks like this, x to the y power. That's your exponential function key. So you type in 1.025, push that key, and then you're going to put in the number 3, which is how many times you do it. And when you do it, you'll get a number somewhat like that. Now, do not write that down. Just leave it there, and just with the calculator, multiply it by 7,000. And you get this number here. And at this point, we'll round off because banks only pay you to the penny. So we're going to round off to the nearest penny. I look next door, and there's a 4-year-old. He's not old enough to go to school, so we leave him behind, and we just leave it at 3. And the answer is $7,538.23. Now we're going to do it quarterly. Well, quarterly means that we're going to do it every 4 times a year, every 3 months. So in this case now, our equation changes. We put in the 4 here. Notice that the 2.5%, we divide it in 4, and we do it 4 times. So it still equals 2.5% for the year. And now, because we're doing it 3 years, but 4 times a year, we're going to end up doing this 12 times. All right? And once again, once we get here, take your calculator out and type in the number. That's our base here. And then the exponential function, x to the y power, that button. And then put in 12, how many times you're going to do it. And your answer should come out something like this. Again, once you get here, do not erase that or you try to write it down. Just leave it alone. And then with the calculator, multiply it by 7,000, and you get this number here. Again, we'll round off to the nearest cent. Next door right is an 8, so 8's bigger than 5, so we're actually going to round up this time to 43. So our answer is $7,543.43. Notice here the difference between these two. Notice that it went up, looks like about $5 more when they compounded quarterly. That's why banks love to compound interest. They get more by doing that. So we would expect when we do it monthly, it's going to even go up higher. So let's do that. Monthly means that n is 12. We're going to do this 12 times a year. So I'm going to take the interest rate and divide it by 12, and I'm also going to do it 12 times every year, so 3 times 12. So we have 7,000, 1.028. This is the 225 thousandths divided by 12. And now you see we really need our calculator to do that. And once again, this is our y to the x button. And now we multiply that times 7,000 and round off. Notice there's a 0 next there, so we're not going to have to round up. So our answer is $7,544.60. And you notice that this is bigger than this, which is bigger than this. So the more times you compound the interest, it's the benefits the bank who's doing it because they're going to make a little more money. Problem 20 asks us, how does the graph of f of x, which equals 3 times 8 to the x power plus 2, compare to the graph of g of x, which equals just 3 to the 8 plus x? Notice the real difference here is that f of x has added plus 2. Otherwise, they're the same. Let me show you first on Desmos what that looks like. You remember Desmos is the program that we can go on, and it allows us to type in a function and see what the graph actually looks like. So I typed in g of x, which is 3 times 8 to the x, and it's the red graph. And f of x is the blue graph. And you'll notice just by looking at it, pick any point here, and g of x is plus 2 higher. If I pick a point here and go up, it catches it here, and it's plus 2 higher. In other words, every point is simply plus 2 higher. So how can we write that in words? And I wrote it this way. I said that every value of f of x will be 2 units greater than g of x. Therefore, the graph of g of x is simply the graph of x added, translated up 2 units. We simply took everything and moved it up 2. It's a translation. #21 gives us a table and wants us to explain in complete sentences whether it represents a linear or exponential function. So what we're looking for is, do the numbers between here and here, are we adding or are we multiplying something to get to each next number? And in our case, when we look at it, we notice there's a common difference. 6 minus 3 and 9 minus 6 and 12 minus 3, we're just simply adding 3 to each one. That means that this is not exponential. It means that this is a linear function. The second part says, well, write it as a function then. Well, remember that a table, a linear function has the form of y equals mx plus b. We know that this function here, 3, is going to be our slope. It's going up 3 each time, so we just need to find the b. So what's the beginning point? Well, we don't have a 0 here, but if we were to go back to 0 and simply go back 3, what would it be? And notice that if we subtract 3 from the first number, the point would be 0, 0. So that means b is 0 and m is 3. So we can write our function as y equals 3x plus 0, or leave off the 0 and just put y equals 3 of x. In problem 22, we're given the function f of x equals 2 to the x power over the domain, that's the x values between 0 and 6, and they want us to find the average rate between 0 and 2, 2 and 4, and 4 and 6. So first we have to fill in for each of the numbers what's the value. So when f of x is 0, 2 to the 0 is 1 power. 2 to the 1 power is 2. 2 squared is 4. 2 cubed is 8. 2 to the 4th is 16. 2 to the 5th is 32. And 2 to the 6th is 64. So there's our values. There's our domain 0 through 6. And our range goes from 1 to 64. Now they want us to find the average rate of change for each interval. And so what we're going to do is we're going to take the f of the 2 between 2 and 4, between these two here. We're going to take the f of 2, or 4 minus 1, and over 2 minus 0. So that's going to be 4 minus 1. These are our values here, 4 and 1, and over 2 and 1. Okay? So 4 minus 1 is 3 over 2, and so that's the rate, that's the average rate of change for that one there. Now when we go to do between 2 and 4, same thing, but now our values are 16 and 4. So when I look at the function at 4 minus the function at 2 divided by the x's, 4 minus 2, I get 16 minus 4 over 4 minus 2, or 12 over 2, or 6 is our average rate of change over that interval. Finally, we go to 4 and 6. Between 4 and 6, it goes from 16 up to 64. So once again, we're looking at those values. The function at 6 minus the function at 4 divided by 6 minus 4. So we get 64 minus 16 over 6 minus 4, 48 divided by 2, or 24. They want you to contrast then the average rate of change. What's happening as this thing is going up? And notice that the change is going from 3/2 to 6, it's going up. From 6 to 24, it's going up. So we have an interval that is, our average rate of change is increasing as x increases. You remember this function looks something like this. And notice at any point the rate, if I drew a line here, the slope of those lines is getting bigger and bigger and bigger. So in this particular exponential function, the rate of change is not constant like a linear. It's always going up. It's increasing. Problem 23, we're asked to solve this by graphing. And what we're going to do is we're going to split the two equations into two. We're going to have one equation that says y equals that, and one equation that says y equals that, and we're going to see if they ever intersect. So I'd choose the first equation, y equals 0.5 to the x power. This is also y equals 1/2 to the x power. So notice this is going to be, when it's to the minus third, I'm going to divide by that, and I end up with getting 8. If you're not sure about that, what I'm looking at here is I can do it this way and say, what's 1/2 to the minus third? Well, that's the same as 2 over 1 to the third power, which is 2 to the third, which equals 8. So similarly, when I have squared to the minus 2, that's going to be 1/2 to the minus 2, or 2 squared, or 4. And to the negative 1, it's just going to be 1/2 to the negative 1, or simply 2. And obviously, when you get to 0, it's 1. And finally, when you get to 1, it's just simply going to be 1/2. So now let's graph those points. If I set out my thing, I know all these numbers are going to be positive, so I set up my x on the bottom. Get me a graph there. And so minus 3, 8 will be here. Minus 2, 4 is here. 2. Notice it's just cutting in half each time. And so our last one is here. And if we were drawing the graph, it would look something like this. It's going to come down and go like that. And that's our y equals 1/2 to the x, or 5/10 to the x. Now let's graph the other one at y equals 4. Well, that's simply a horizontal line at y equals 4, and so it graphs just like that. So the question is, where do they intersect? They intersect right here at the point -2, 4. So notice, you can even see it on the graph at -2, it equals 4. And so where does 4 and 4 cross? It crosses at the point when x equals -2. These two graphs cross, so x equals -2 is our solution to this equation that we started with. Problem 24 states that a family purchased a car for $20,000. The value of the car decreases about 20% per year. In other words, it depreciates. After 6 years, the family decides to sell the car. Should they sell it for $4,000? Well, our function for exponential function is y equals a times b to the x power. In this case, we're beginning with 20,000. Our growth rate, or in this case, our decay rate, is going to be 100% minus 20%. In other words, they lose 20% each year. So at the end of the year, their car is only worth 80% of what it started, 100% minus 20%, or the factor b will be 0.8. We're going to look at it what it will be in 6 years. So those are our things we're going to plug into this equation. And we have y equals 20,000 times 8/10 to the 6th power. Use our calculator again. Remember, if you're not used to that, you're going to type in 0.8. You're going to go to the exponential function button that looks something like that, and then type in the number 6. So now we do that, and then multiply by 20,000. And so the value of our car after 6 years will be $5,242.88. Now the question is, should they sell it for $4,000? Well, if you're just thinking about money, the question is, the car is going to be worth more than $5,000, so they shouldn't sell it for $4,000. Of course, they might decide to sell it. Maybe it's a friend. Maybe it's an uncle or somebody or needs a car. Maybe they have a young high school granddaughter that needs a car, and so they'll easily sell it to her for cheaper. But just money-wise, it wouldn't be worth to sell it for $4,000 because it's worth more than that. Our last problem asks us to write the explicit and recursive formula for each of the sequence. Remember, to write each of these formulas, we only need 2 pieces of information. We need to know what's the first term, which is always easy, pretty easy to find out. And then, what are they being multiplied by each time? And that's your common ratio. If you can find those 2 pieces of information, you can write both of the equations. So let's begin with the first one. The common ratio is found by taking 2 successive terms and dividing the second one by the first one. So 84 divided by 14, or 504 divided by 84. Notice they're all equal 6, which means in this sequence, we're simply multiplying each term by 6. So r is 6, and our first term is obviously 14. So now we have all the information we need to write down our formula. Our explicit formula first says that the nth term equals the first term times r to the n minus 1. So I'm simply going to take my first term and plug it in there. I'm going to take my ratio and plug it in there. And so we have a to the n equals 14 times 6 to the n minus 1, and that's our explicit formula. The recursive formula is just as simple. This just says that the nth term equals the previous term, the n minus 1 term, times r. So I'm going to put my r here, and we always have to also state what's the a1 term, so we know where we're beginning at. And so we end up with an equals a to the n minus 1 times 6, and then there's our 14 there. And so there's our recursive and explicit formulas for the first sequence. So let's do it again for the second one. The common ratio again, take the second term and divide it by the first term. It should be the same for all of them. And notice it's 1/2, or in other words, it's being divided by 2 or multiplied by 1/2. My initial value is 200, and so I can write the explicit formula. Again, plug in the 200 in for A1, put that in your R for R, and your answer is a to the n equals 200 times 1/2 to the n minus 1 function, and that's our explicit formula. And again, the recursive, we put in the r there, and then we also state again that the a1 starts at 200. And so there's our answer. All right? So that finishes the review. I hope you do a great job on your unit test.